Professor Aspect was born in 1947 and was an alumni of the École Normale Supérieure de Cachan and the Université d'Orsay. He took in 1985 a research position at École Normale Supérieure Collège de France. Since 1992, he has been a CNRS senior researcher at the Institut d'Optique. He is now a professor at the Institut d'Optique Graduate School, chair Augustin Fresnel, and at the École Polytechnique in Palaiseau. He is a member of many academies, l'Académie des Sciences Paris, France, l'Académie des Technologies française, la National Academy of Sciences USA, the Österreichische Akademie von Wissenschaften Austria, Académie Royale de Belgique, and Royal Society. He got many awards, received many awards, the CNRS Gold Medal, 2005, the Wolf Prize in Physics, 2010, the Tommasoni Award, 2013, the Balzan Prize on Quantum Information, 2013, the Niels Bohr Gold Medal, 2013, and the Albert Einstein Medal, 2013. On his research, Professor Inguscio will give more information. I just want to welcome Professor Aspect in our academy and also tell you that I got a letter from the Fondazione Internazionale Balzan, where the presidents, Professor De Cleva, and the president of the committee, of the prize committee, Professor Salvatore Vecca, say that they are very happy that we invited here Professor Aspect because he was a recipient of the Balzan Prize in 2013, as I said, and they apologize for not being able to attend his lecture. So welcome, Professor Aspect, in our academy, and I give you now the word to Professor Marco Gilli, Rettore del Politecnico di Torino.
Yes, good morning. Thank you, Alberto. It's a pleasure to be here and also to welcome all of you here for this very exciting and very interesting lecture of Professor Aspect. Well, there are many reasons why the Politecnico di Torino is here. Of course, the first reason is that we are going to award Galileo Ferraris Prize, and you know that Galileo Ferraris was a professor in the Politecnico di Torino. At that time, it was not yet named Politecnico di Torino. It was the Regal Industrial Museum, but Galileo Ferraris was the first professor of electrical engineering. We still have the name electrotechnics, which is not in English, but he was the first professor of electrical engineering. He also founded the associations of Italian electrical engineers, and of course, he was one of the most brilliant scientists, in addition to some others that have been here in this academy, like Lagrange. He was one of the most brilliant scientists of this region. There is a second reason, of course, we are very happy to be here, and is that this is the International Year of the Light, and you know, more and more in technical university, we realize that now, the principles of quantum physics are coming into technology. And we have a lot of activity regarding photonics, but if you think to all the disruptive technologies that will have a great impact, both economical and social impact. So you find that photonics, additive manufacturing, and so require now, in some way, to merge together fundamental physics and technology. And this is a real challenge for the future. I'm sure that in the future, more and more of our activity in technical university will concern quantum science and quantum technology. So that's why, there's another reason, we are very happy to be here. And finally, the third reason is that since many, many years, since the time in which the INRIM Institute was split in two parts. One part was Colonnetti and the other part, was entitled to Galileo Ferraris. There has been a very strong collaboration between our departments in the Politecnico di Torino and the department and the sections of the Galileo Ferraris Institute. There are some schools of the Politecnico di Torino, like the School of Electronics and the School of Computer Engineering, that were founded exactly by professors that were researchers in the Galileo Ferraris. So there's been a very, very strong connection between INRIM and the Politecnico di Torino. And in the future, we think that this connection could be strengthened just by focusing on some subjects that are related to, in some way, to the lecture of Professor Aspect and to the field of quantum science and quantum technology. So it's really a pleasure to welcome here and to thank Professor Aspect for coming here, for honoring us with his presence here in this academy and in this city. And I thank you for your attention.
Visto che abbiamo celebrato qualche giorno fa l'anniversario di Dante Alighieri, quindi dovrei dire io fui terzo fra cotanto senno. I would like to take the opportunity of one of the last statements of the rector Marco Gilli to say that essentially with Galileo Ferraris, you in Piedmont and we in Italy had a qualitatively magic moment. That was the moment when something which was abstract, a sort of conceptual story, like the Maxwell equations, they turned out to become technology, with the story of production of electricity from a very nice equation. Now, the reason why today we are eager to give this prize to Professor Alain Aspect, who since now I will call Alain, will be maybe explained later, but essentially it is because there has been one of the others many real magic moments in physics, and this happened in around 1981 or 3, where quantum mechanics was still a conceptual debate, was a philosophy, probably was the most important philosophical revolution of the last century. And the debate, I see a specialist, so I don't want to enter this field, but the debate was whether there was possibility to have hidden variables on the non-separability of the variable. I'm using, technical stuff. Essentially, that, and I think that Alain will explain this. There was all the debate on the validity, the completeness or no of the quantum mechanics. But sometimes the revolutions comes as a consequence of surprises. So I was a student in Pisa when my professor Gozzini, we did the history, essentially asked us young people to come and talk a little bit with this young guy coming from Paris, making the PhD on his own idea, which was a totally strange idea, so totally new. And the idea was to put together an experiment to see whether it was possible to transform a Gedanken experiment into a real experiment. And this was made possible by an inequality that Bell had written, and so on. So, first of all, this is a demonstration of how young people, when they are brave, or few of them are brave, they are able to, to go in a new direction. I think it had not much support in general in the French, everywhere. A classical, environment. Then he made really this experiment, and immediately, and I imagine that he will talk about this. Immediately, he essentially made possible the realization later on of the far-seeing idea of Richard Feynman, who in '82, with a huge fantasy, he had written about the possibility of putting together a quantum computer or a quantum simulator and so on. Now, a quantum computer is possible, or might be really possible, because of the entanglement, and which is this strange word, entanglement, that in French is intrication, and in Italy, we don't translate, because the French, they have to translate everything. Computer into ordinateur, entanglement into intrication. So he demonstrated the possibility with this experiment of this revolutionary thing of the l'intrication quantique, which now makes possible essentially all the quantum technologies, and in particular the quantum metrology. Tomorrow we are going together to a special roundtable which is in Brussels, where the idea is to show that now really more and more precise measurement and test and real technology can be done according to the surprise that he produced for all the world, that really that crazy experiment of having two photons leaving an atom of calcium going one left and the other one right, they still remember essentially each other. There was a correlation between the two. So this was essentially, this is a revolution. Making possible is the key story. This is the reason why he got the Balzan Prize. Making possible what Marco Gilli was saying, that now quantum mechanics is becoming a real technology. Pay attention, not the technology like the laser one, because the laser is, of course, is a consequence of quantum mechanics, or even the transistor. But there we are using the laws of quantum mechanics to create a tool. Here, the quantum mechanics itself is becoming, a technology. Alain has written many books, but also together with a few Nobel Prizes is co-author of a book in French, Demain la physique. So what will be the physics demain? And I think that no one in the world is good as him in talking what could be in the future, because this book is full of ideas again, which assure the progress of science for the future. Then I would like, my president has already made the long list of prizes. He has got all the prizes. So, but one who knows, and even Italy has awarded him an important international prize. The University of Rome has an international prize, so I must say that Italy has recognized him as a great scientist. But let me conclude telling why we thought that this prize had to be offered to him in this academy. One of the many lectures that has been given in the past, this has been in Berlin, in the villa, the little villa of the German Physical Society, where Lagrange, which was the house of Lagrange. And this talk was given in the frame of something organized between Italy, Germany, and France, in honor of Lagrange. So I assisted to a wonderful talk of Alain, the French, invited by the Germans in the house of Lagrange, with myself as the Italian making the, the introduction and the comments. So I think that it's absolutely necessary to have this award given to Alain, in this place, because really, we are talking of revolutionary ideas in this sort of, a European scale. So this is what I wanted to add to what already the President and the Rector have said, and so probably at this point I think that Alain, you could start, or I give the word to the President.
Yes, well, thank you, Professor Inguscio, thank you, Professor Gilli. Now I'm very glad and happy and proud to introduce Professor Alain Aspect, who will speak for his lectio magistralis on the topic From the Einstein-Bohr debate to Bell's inequalities tests, precision measurements, settle a conceptual debate.
Okay. Yes, so I think that what is interesting in the story I'm going to tell you is that really it's a story that goes from concept to technology, from conceptual debate to precise measurements, and I think it covers all the different sides of science, the most conceptual, the most technological, and precision. So I like to have a subtitle which is From the Einstein-Bohr debate to quantum technologies, are we living a new quantum revolution? And I have a prejudice that yes, we are living a new quantum revolution. So let us start with the emergence of quantum technologies, and more particularly quantum information. If you Google quantum informations, you have hundreds of millions of results, and I've selected a few of them. There is a journal on quantum information. The New York Times speaks about quantum information. I'm sure that Italian newspaper also speak of quantum information, not French newspaper. French newspaper are not interested in science, but I think that you are more civilized than we are. There is an Institute for Quantum Information in Caltech, in MIT, in Cambridge, UK. So really, it seems to be an important thing. But how did it emerge? Well, I think here we have the main actors. Einstein and Bohr, the big debate between Einstein and Bohr, I will explain more in detail in a while. Schrödinger, who added his grain of salt exactly at the same moment in 1935. Schrödinger was certainly among these big people, was certainly the one who immediately understood the importance of the debate between Einstein and Bohr. And then John Bell, who 30 years later, that is to say in 65, totally renewed the debate. And what did they find? They find that entanglement is different. Different from what? Different from what usually we think of the strangeness of quantum mechanics. When you think of the strangeness of quantum mechanics, you think of wave-particle duality. No doubt, this is strange. But what these people realized is that entanglement is different. And it took a long time to be recognized. Believe it or not, when I started my PhD, as Massimo evoked, so in 74, 75, most of the people who tell you, look, Alain, what you want to demonstrate, we know already. It's wave-particle duality. And I say, no, entanglement is not the same thing. It took a long time to be realized, and these people are people who realized it. And then Feynman, you mentioned it, in 82, Feynman recognized that entanglement is different, because if you read lectures on physics, he say, all the mystery in quantum mechanics is in wave-particle duality. 20 years later, after lecture on physics, he said, there is something new, entanglement. But Feynman, being Feynman, as soon as he recognizes that there is something new, he invents a way of applying it, and it was the invention of the concept of quantum computation. So entanglement not only is different, but it is more. Okay. So now it will be the main part of my talk. I will talk about the Einstein-Bohr debate, Bell's inequality test. And here I have some references. This is a wonderful book with a text of John Bell about the concepts of quantum and the conceptual debates of quantum mechanics. This is a wonderful book. This is a book by Nicolas Gisin, which I think it's a quite good book about the foundation of quantum mechanics. He puts the emphasis on the dramatic character of randomness in quantum physics, and I think that is fully right. So this is why it's called quantum chance. There is also a lot of quantum non-locality. And this textbook on quantum optics, I am one of the authors. So if you buy it for your library, I get some royalties. You know, I can pay for 1 or 2 cups of coffees, so it's good. But the important thing is that in this book, you have all the calculations which allow you to get the result I will cite here. If you don't want to pay for the book, you can go to my homepage and you can download these calculations for free. Okay, so make your choice. Okay, Einstein and quantum physics. I'm sure you know that Einstein is really one of the founders of quantum mechanics. We should not forget that. Of course, we know of Planck, 1900. But Planck in 1900 was desperate, and this is why he called this constant H for zu Hilfe, help, you know. He was desperate, and he did not like at all the hypothesis made that exchanges of energy between radiation and matter are quantized, okay? But he did not like that at all. Einstein in 1905 made a strong hypothesis that radiation itself is quantized, not only the exchanges, radiation itself. So we should consider really Einstein a major founding father of quantum mechanics, okay? And remember that he got the Nobel Prize for his hypothesis that radiation is made of Lichtquanten, okay, as he said. He did not use the word photon, he said quanta of light, Lichtquanten. In these years of light, it's appropriate to remember it. But you know what happened? Einstein was more and more dissatisfied in the way quantum mechanics was developed, and more precisely in the philosophy of the people who were developing quantum mechanics, the so-called Copenhagen school, okay? He was really not happy. He had no problem with the mathematical calculations. He was unhappy with the interpretation. And he came with plenty of objections precisely about wave-particle duality, plenty of objections about the Heisenberg so-called uncertainty relation. And for this, I must say, that Niels Bohr could always reply to Einstein and show that Einstein's objections did not stand. The Copenhagen interpretation was really consistent to describe wave-particle duality and Heisenberg uncertainty relation. And then, in 1935, Einstein came with totally different objections. It's the famous Einstein-Podolsky-Rosen problem that I will describe now. This objection was underestimated a long time until Bell, and entanglement is now at the core of quantum information and of a part of quantum metrology. So what is the equation that Einstein was asking in 1935 with his colleagues Boris Podolsky and Nathan Rosen? Excuse me. The equation is the following. You all know that in most situations, when you do a calculation of quantum mechanics, you get a probabilistic result. The probability to find the spin on the up dot is 40%. The probability to find it down is 60%, etc. And so Einstein was asking the question, is it possible to explain the probabilistic nature, character of quantum prediction by invoking a supplementary underlying level of description. What does it mean? Think of the Maxwell-Boltzmann distribution of the velocities of the molecules flying here in the atmosphere, okay? We have no problem no conceptual problem, because we think that it is convenient to use a Maxwell-Boltzmann distribution, but we have no doubt that each particular molecule has a well-defined velocity, and it's just a convenience to describe it by a law of probability. So Einstein has a question. Isn't it the case that the statistical nature of the prediction of quantum mechanics tells us that there is an underlying description, more precise, where each object would have a precise behavior, and it is convenient to have a kind of statistical theory. And Einstein thought that with the reasoning I'm going to describe now, he had found a positive answer to this question. And we will see that Bohr immediately was strongly opposed. So let us describe an Einstein-Podolsky-Rosen Gedanken experiment. At that time, it was really an ideal experiment. And it's not exactly the scheme that Einstein was describing at that time. I prefer to describe immediately in the modern form with photons, because it is this form which has been realized in real experiments. So what do we have? We have a source emitting two photons, a photon to the left, a photon to the right. I show them with different colors to avoid the confusion that the problem stems from the indiscernibility. Here, they are perfectly discernible. This one has a color, this one another one. You put a filter here, a filter, you know which photon is which. So no question of indiscernibility. Now, on this photon, you make a measurement of polarization, so you can think that this is a birefringent crystal or Wollaston prism or whatever. What does it mean? It means that you have an optical axis here, and if the polarization is parallel to the axis, the photon will be found in the +1 channel, and if the polarization of the photon is orthogonal to the direction of the axis, you will find it in the -1 channel. And now, of course, the question, which immediately takes us to the probabilistic character of quantum mechanics, if you have a beam of light, a macroscopic beam of light, and if the polarization is at an angle of this axis, a fraction of the beam will go up and a fraction of the beam will go down, and it's a Malus law, etc. But if you have a single photon, the photon cannot be cut in two, okay? So if the photon has a polarization which is neither parallel nor perpendicular to the axis of the polarizer, there is a certain probability to find the photon up and a certain probability to find the photon down. So we can define probabilities P plus A, which means probability to find the photon in the channel +1 when the orientation is A, etc. More interesting is to consider the joint probability that the first photon is found here and the second photon is found there. I should have said that I have another polarizer in orientation B for the second photon. Okay. So the joint probability P plus of AB is a probability to find +1 here and +1 here when the orientation are A and B. Okay, and I have these four probabilities. At this point, it's just an experiment. We can think of it. There is no Einstein-Podolsky-Rosen yet. Now comes Einstein-Podolsky-Rosen. The discovery of Einstein-Podolsky and Rosen is that the standard formalism of quantum mechanics, just using the basic principle of quantum mechanics as explained, for instance, in the book of Dirac, okay, at that time the book did exist already, the formalism of quantum mechanics allows you to consider that state. What is this state? Let us spend 1 minute on it. Here you have the axis. Here I describe only the polarization part of the wave function describing the two photons, okay? I don't describe the propagation, etc., etc. Okay, I just concentrate on the polarization part. X corresponds to the first photon polarized along the axis X. The second X here corresponds to the photon nu2 polarized along X. So XX describes a pair of photons polarized vertically. YY describes a pair of photons polarized horizontally. What Einstein, Podolsky, and Rosen say, look at the basic principle of quantum mechanics. We are allowed to consider a state like that, which is a superposition of vertical, vertical, plus horizontal, horizontal. And they say, this is really very strange, because don't make any confusion. This does not mean that you have a pair of photons with a polarization at 45 degrees. No, no, you cannot. You cannot factorize this state as a product of a state describing the first photon times a state describing the second one. Mathematicians have no problem to show that this cannot be factorized. You are in a space which is a tensor product, and it is well known that in a tensor product state, most of the vectors cannot be factorized. Okay. Now, starting from this, it is quite easy to calculate the probabilities of the various results here. So we assume that we can produce a pair of photons like that. What are the predictions of quantum mechanics? So at this point, you go to my book or you go to what you download on my homepage. It's not very difficult. I would say it's third or fourth year of university, okay? What do you get? First, single probabilities, P plus, P minus equal 1/2, whatever the orientation. That is to say, these photons appear as totally unpolarized. Whatever you do, you get 50% chance to get plus, 50% chance to get minus, and whatever the orientation. Same on the other side for the second photon. Now, when you look at the joint detection, now you have interesting formulae as a function of the orientation of the two polarizers. It depends on the angle between the two polarizers. AB is the angle between the two orientations. And so let us focus on the special case where this polarizer and this polarizer are parallel. That is to say the angle is 0. When you look at this formula, you find P plus plus equals P minus minus equals 1/2, and P plus minus equal P minus plus equals 0. This does not look interesting, but it is very interesting. It is very interesting because it tells you that the results of the measurement are totally polarized, totally correlated, excuse me. Why do I say that? 1/2 doesn't look totally correlated. Yes. Remember that the probability that the first photon gives plus is 1/2. And now the joint probability is also 1/2, which means that the conditional probability is 100%. In other words, this photon arrives here. There is 50% chance to find it here, 50% chance to find it there. But if you find the first photon here, you are sure to find the second photon on +1. And if you find this one on -1, you are sure to find the other one on -1. And if you are not yet convinced of this total correlation, P plus minus equals 0. Never you have +1 here and -1 there. So it's just like you have coins, head or tails, but if you get head here, you are sure to get head here, so it's a total correlation. Okay. So we have that. Because we are serious people and we want to make real measurements, we are not happy just with hand waving and saying total correlation. We want to have a real measurement of the level of correlation, and for that we have a standard and classical definition. We consider the result of measurements here as a random variable, the result of measurement there as a random variable, and we look at the correlation coefficient between these random variables. Classical definition, average of the product minus the product of the average. If there is no correlation, this gives 0, and you normalize, okay, to have a number between +1 and -1. So when you do that, you have a formula, and now when you insert into this formula, which is classical, when you insert the prediction of quantum mechanics, then you get a coefficient of correlation, of polarization, which is cosine of 2 times the angle between the polarizer. Whatever it is, this is the result. You can check immediately that if the angle is 0, you find 1 total correlation. If the angle is 90 degrees, you find -1. It is very easy to understand. Why -1? Because since the polarizers are crossed, if you get +1 for the first polarizer, you are sure to get -1 for the other one, so, okay. Total correlation again, etc. So now we have a real prediction of quantum mechanics that we can test. Okay. So this is the prediction. And when you are a naive physicist, like me, I'm really a naive physicist. I like simple images. You say, okay, strong correlation. I don't believe in magic. And so I want to understand why I have a strong correlation, okay? So this is my job as a physicist to understand. Somebody turns a knob here, there is an effect there. I want to understand why there is a correlation between the fact to turn a knob here and to have a result there. So correlation, I want to understand. How can I understand it? Well, the first idea is to say, okay, you have made a calculation, look into the calculation, and the calculation will give you an image. Well, it turns out that it is not so simple. Because if you look at the direct calculation, which implies doing a projection into the Hilbert space, which is a tensor product of the space of the first photon by the space of the second photon, this is happening in an abstract Hilbert space, very difficult to make an image in our real space, okay? So it's annoying, and I like to cite an important sentence in the book of Asher-Perez. Asher-Perez was a strong defender of the Copenhagen interpretation of quantum mechanics, very orthodox. He was a very good theorist. However, he writes, quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. So I cannot be satisfied with an image which is only in a Hilbert space. So let us try to make an image in real space. And there is a way to do it. And the way to do it is to assume that this polarizer is closer to the source than the other one. So I have first a measurement here. So I am in my lab. Here I can describe in the real space. And the result of this measurement can be either +1 or -1. Okay, so let us suppose I get +1. What do I do now? Now I have a famous collapse of the state vector. By the way, this calculation is absolutely orthodox, okay? It's Cohen-Tanuji approved, okay? I can show you all the pages of the book of Cohen-Tanuji. I'm only using standard orthodox quantum mechanics. So after the measurement, there is a famous collapse of the state vector. And so what it tells me is that if I add plus for the first photon, then immediately after this measurement, the state of the two photons is ++. Now it's interesting, because now it's a factorized state. So if I found this polarization for the first photon, then immediately I know that the other one has the same polarization. But if I have found minus, which means perpendicular, immediately after the measurement, the other one is polarized perpendicularly. That's the result of the calculation. And now this result I can describe in our space, okay? And then the calculation, you can continue, because once you know that the second photon has a given polarization, plus in the first case or minus in the second case, you just go on, and then it's just a question of applying the Malus law for the second measurement, and then you find exactly the same results at the one. It's a little more complicated, okay? So if you are a student and you take an exam, it's better to do the first calculation. But if you want to understand, maybe the second calculation is better. And so what you get at the end is that you get the same result as done with a direct calculation, but there is something strange. The measurement on the first photon seems to influence instantaneously at a distance the state of the second photon. So now I have an image in our state, but there is something strange, something that you know, most of you know, is called quantum non-locality. I do something here, and instantaneously it seems that something happens there. Very bizarre. And of course, Einstein could not accept that, because Einstein, you know, causality, relativistic causality, etc. Okay, so when you face this, you say, what can I do? Well, in fact, I can realize that there is another way for understanding this correlation. And this way of understanding correlation is very simple. you have two objects which were created at the same place. Then they travel, they go away, okay? And you do a measurement here and a measurement there, and you find correlated measurements. Obviously, this can be related to the fact that the two objects had a common property from the first moment when they were created. Think of medical doctors. They look at some disease on twin brothers. When they find that the disease has the same probability to happen for the twin brother, they say, okay, the explanation is very simple. They have the same genome, the same chromosomes, okay? So there is a very simple idea for understanding this correlation that when the two photons are emitted here, they have a common property, lambda, and this common property, they have the same value for lambda, and when you make the measurement here, it depends on lambda. When you make the measurement there, it depends on lambda, so no surprise that you find the same result. For instance, so this image is simple and convincing, okay? But Bohr disagreed. Why did he disagree? Because when you invoke such an image, which is really very natural, very scientific, okay? But when you invoke such an image, you complete quantum mechanics. You say that the state vector is not enough. All the pairs of photons are described by the same state vector. But if I start saying that there are lambda parameters, it means that certain pairs, for instance, are from the beginning polarized like that. There are other pairs which from the beginning are polarized like that, etc. So I say there are different kinds of pairs. So I say that I have to complete the formalism of quantum mechanics. So this takes us back to the initial question. Isn't it the case that quantum mechanics is only a statistical theory and we have an underlying level? Now we come to the conclusion that to understand this strange correlation, we need to invoke this underlying level. This was a point of view of Einstein. But Niels Bohr thought that it is impossible to complete quantum mechanics. If you would complete quantum mechanics would be more or less inconsistent. The problem in this discussion between Einstein and Bohr is the following. When you read Einstein, it is crystal clear. So you are fully convinced that he is right. And when you read Niels Bohr, it's really impossible to understand what he means. You know, he's famous, Niels Bohr, for that. I mean, it's not a criticism. He's famous for that. Niels Bohr was mumbling and having very long sentences, and even when you read his paper, it's very difficult to understand. I can tell you, I've read all these papers about the EPR debate, okay? Einstein is crystal clear, Niels Bohr is impossible to understand. It's not a joke. Niels Bohr once said, you know, he was always talking about complementarity of this and that, etc. And once he said that truth and clarity are complementary qualities, okay? And he did his best to be as true as possible. So clarity, forget about it, okay? So the problem with this, but what I can say, honestly, after reading all these texts, is that Niels Bohr had a deep intuition that he could not accept to complete quantum mechanics as Einstein wanted to do it, but he could not demonstrate that it was impossible. So what happened? The debate between Bohr and Einstein lasted until the death of these two great physicists, really. Until the end of their lives, they exchanged letters and they discussed. This is a visit of Bohr in Princeton and discussing with Einstein, okay? But without much attention from a majority of physicists. Why? Not because they were stubborn. Look, you are a young physicist. There is a new theory, quantum mechanics. You apply it to plenty of phenomena and it works wonderfully, okay? With quantum mechanics, you can explain the mechanical properties of matter. You can explain the electrical properties of matter. You can explain the optical properties of matter. You can explain everything, chemical bonds, etc., etc. So it's really a fantastic theory. You have heard that there is a discussion between Einstein and Bohr, but look, these are old guys, okay, good that they discuss, especially because according to what you have heard of their discussion, they don't disagree on the calculations. They only disagree on the interpretation. So you are an active physicist, you use quantum mechanics, you know that there is a debate, but the debate is not about the mathematics, so you use the mathematics. That's okay. So we have to say that nobody cared, okay, about a few people. Well, Schrödinger had been really writing about this, but most of the other physicists did not care, okay? And then 30 years later, well, 29, but almost 30, John Bell came with a fantastic finding. The finding was the following. If you believe in the interpretation due to Einstein, if you believe that this correlation can be understood by invoking a common property between the two partners, between the two particles, then you have an interesting consequence, which is a quantitative consequence. The idea is the following. Bell writes the idea in a very simple manner. He says, okay, when the two photons are emitted, there is a set of parameters that I call lambda. Lambda can be a complicated mathematical object, doesn't matter, okay? Now we admit that the result of measurement here depends on the value of lambda, which is brought by this photon, and depends on the orientation. So you introduce a function, capital A of lambda, and of the orientation A, which can take only two values, +1 or -1. By the way, nowadays there is a frenzy about Bell's inequality, and regularly there are papers of people who say, oh, I have a strange result about Bell's inequality. When they are and it disagrees, it shows that Bell was not right, etc., etc. Usually these people forget that we want to have a dichotomic function, a function which can return only either +1 or -1. So this is crucial, but it is what we get here. When you send a photon on a polarizer, you get either +1 or -1. You don't get anything in between. So similarly on the second polarizer, you have a response, which is a function with value +1 or -1, depending on lambda, the same lambda as the first photon, and the orientation B. And of course, you have to describe how the various pairs are created with a certain lambda or another lambda, and you describe it with a density of probability, which is a normal density of probability, that is to say a positive and normalized function. And with this, you can calculate, for instance, if you have the explicit value for this function, you can calculate, for instance, the correlation of polarization. It's not difficult to find that it is this value, nothing else than the average value of the product AB. Okay. Let us take a very simple example. Let us assume that when the two photons are created, they are created with the same polarization. Whatever it means. We think that we understand what is a polarization. So they are created with a certain polarization. Now, I need to invent the function, capital A. Well, looks complicated, but it is very simple. If the polarizer is aligned with the polarization of the photon, we will find +1. If it is at 90 degrees, we will find -1. And if we are in between, we put the frontier at 45 degrees. So if the polarization of the photon is closer to the axis, we get +1. If it's closer to the perpendicular, we find -1. Cannot get a simpler model, okay? In addition, we assume that the distribution of the pair is fully isotropic. Why? Because we know that the quantum result is rotationally invariant. So we take something isotropic. With this, you make the calculation, and you get the red line which is here. This is the value of the coefficient of correlation calculated with this very simple model, and you get this, and the quantum result is cosine of 2 times. So you see it's not bad for such a simple model. So then you go and you meet your friend, which is an applied mathematician or a theorist. He knows everything about Bessel function, Hankel function, all these special functions, and you tell him, can you design a model with more sophisticated functions that would reproduce everywhere the prediction of quantum mechanics? So is there a better model agreeing with quantum mechanics in all orientation? And the answer is given by Bell's theorem, and this is Bell's theorem, no. There is no model which can reproduce all the prediction of quantum mechanics. How does it work? What Bell, so there is no, I will explain the words, local hidden variable theory in the spirit of Einstein idea that can reproduce quantum mechanical prediction for all orientation. So here is an example of what I mean by cannot reproduce for all orientations. It reproduces here, 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 but here there is a slight difference, okay? So, well, that's the way it is. How does it work? What Bell could demonstrate is that if you assume that the correlation can be explained with lambdas, capital A and capital B, not the special model, any model with any form of lambda, capital A, capital B, and function rho, then there is a quantity S which cannot be larger than 2 and which cannot be less than -2. And this quantity S is quite interesting. It's a combination of 4 correlation coefficients considering 2 orientation, A and A prime for the first polarizer and B prime for the second polarizer. So you make a measurement AB, then you make A B prime, A prime B prime, and the last one is probably A prime B, okay? So you make 4 measurements, okay? You put the first number into this, and according to this Bell theorem, if you can understand this correlation invoking supplementary parameter lambda, this cannot be bigger than 2. On the other hand, remember the quantum expression for the EPR situation. It's cosine of 2 times this angle. So let us take this particular set of orientation. AB equals pi over 8, etc. Pi over 8, pi over 8. 2 times pi over 8 is pi over 4. I'm sure you follow me. Cosine of pi over 4 is 1 over root 2. So you get 1 over root 2, 1 over root 2, 1 over root 2. Now look at A, B prime. If you double the angle, the cosine is minus 1 over root 2. But there is a minus sign. So I have again 1 over root 2. So for this specific set of orientation, the quantity S predicted by quantum mechanics is bigger than 2. Hence, Bell's theorem, there is no model based on lambda, A, B, etc., which can reproduce all the prediction of quantum mechanics. Okay, let us continue. So now, the possibility to complete quantum mechanics according to Einstein idea is no longer a matter of taste. It has turned into an experimental question. Okay, as somebody said, if you find a conflict with quantum mechanics, which is a so well-established theory, why don't you consider again the demonstration of your conflict? So there are dozens, probably hundreds of papers of people who try to say, where does the conflict come? It seems fair to me, after reading not all of them, but a large number of these papers, that these are the necessary hypotheses to obtain Bell's inequalities, that is to say, to obtain a conflict with quantum mechanics. First, you must introduce the idea that each photon leaves the source with a property or a set of property determined that you can describe by a mathematical object, lambda, and the 2 photons, when they leave the source, they have the same set. That's the idea. Otherwise, I mean, that's the idea of understanding this correlation, okay? And the second idea which is called the local realist worldview, is that the result of the measurement that you have here will only depend on this set of parameters, lambda, carried along by this photon and by the orientation of this polarizer here. And this is very important, and it is a local realist worldview. And then Bell realized, when he was demonstrating his inequality, that in fact this implies what is called Bell's locality condition. It implies that really the result of the measurement here is not allowed to depend on the orientation of the other one. If it could depend, then you could not demonstrate Bell's inequality. So this is called Bell's locality condition. But in the same paper, Bell immediately noticed the following fact. He said, look, if while the two photons are traveling from the source to the polarizer, if you change rapidly the orientation of the polarizer, then there is not enough time for this information to go to the other side. So if you could change rapidly the orientation of the polarizer while the photons are in flight, then this locality assumption would be guaranteed by the laws of relativity. And clearly, when you read Einstein, there is always implicitly this hypothesis that when objects are space-like separated in a relativistic sense, then what you do here cannot instantaneously affect the other side. So this is what Bell says in his paper, and now we have clearly a conflict between quantum mechanics and Einstein's worldview. The Einstein's worldview is called local realism. That is to say, the fact that when I have an object here, I do a measurement here, all the result of the measurement depends on the property of the object plus the setting of my measuring apparatus here, and everything which is in the backwards light cone, but not things which are out of the backward light cone. Okay. So now it's time to go to an experimental test. Surprisingly, in spite of all the wonderful achievements of quantum mechanics and all the wonderful experimental developments, there was, at that time, no experimental result available to test Bell's inequalities. And the reason is that Bell's inequalities are extremely general. Basically, any kind of correlation you can think of will obey quantum mechanics. Not only classical correlation, like the twin brother with chromosome, or if you have mechanical correlation that you can explain by classical mechanics or classical electrodynamics, but even correlations that you calculate with quantum mechanics, in most of the cases, they don't violate Bell's inequality. It's very rare that you find a situation in which you predict the violation of Bell's inequality. And so for this reason, they realize that it is necessary to find a situation where the test is possible, and this was a great achievement of Clauser, Horn, Shimony, and Hall in '69 to show how with photon polarization you could find a situation which is exactly the situation that I have described. There were 3 generations of experiments. The pioneers in '72, there was one experiment in Berkeley, Clauser and Friedman, one experiment in Harvard, Holt and Pipkin, and it was very interesting because in '72 they got opposite results. Berkeley obtained a result in favor of quantum mechanics and violating Bell's inequality. In Harvard, they found agreement with Bell's inequality and disagreement with quantum mechanics. Then in '76, there was an experiment in Texas, A&M, you know what is A&M, agriculture and mining, which is kind of interesting. But you know they were in the center, so they say, and in this experiment they found quantum mechanics. The problem with all these experiments is that if I would describe them, you would not recognize the schemes that I have shown. I mean, at that time, due to technology, the experiments were quite different from the ideal scheme, which means that you need supplementary hypotheses. Moreover, in the first experiment, the rate of data was so low that it took weeks to accumulate the data. So let's say it was wonderful experiments, but it's not really surprising that there were conflicting results. This is why in '75, I embarked into a series of experiments, and the goal was to build a source of entangled photon extremely efficient in order to allow me to do measurements in schemes closer and closer to the ideal scheme. And I will describe it. So these experiments were completed in '82. As Massimo said, it was my PhD thesis. And then a new generation of experiments started by the end of the '80s with new type of sources of entangled photon, and it's still going on, and I will say a few words about that. So let us say a few words about the experiments I developed for my PhD thesis. The main idea was the following. This is the scheme producing the two entangled photons that had been discovered by Clauser and company. So the idea is that if you can excite an atom, in that case it's calcium, but doesn't matter, with an angular momentum J equals 0 and weight, it will decay through J equals 1 and J equals 0, and then because there are two different paths to decay, what you obtain is a linear superposition of this, which is a sigma plus, sigma minus polarization, plus that, which is sigma minus, sigma plus, and when you express the circular polarization as a function of the linear polarization, you get exactly the state you want to have. The difficulty is to excite this state. In the original experiments, you cannot do it by direct absorption of an ultraviolet photon because the two levels have the same parity. And so what they did was exciting the atom to upper lying level and waiting. And when they waited, from time to time, there was an atom decaying through this route, and they got a pair of entangled photons, but most of the time, there was another route, and then finally it came here, and you had the second photon, but not the first one. So it was a very inefficient source, and plenty of other problems with the source. So what I did, because of the progress of technology, there were the new lasers, there were tunable lasers. What I did was exciting directly this transition by adding two photons. The two levels have the same parity, so I can effect a two-photon transition. At that time, it was really state-of-the-art, and it worked, and the source was beautiful. I told you that in the experiment of Clauser, it took days and weeks to have a significant result. Look how many I had. I obtained 100 real coincidences per second, which means in only 100 seconds, less than 2 minutes, I had 10 to the fourth. 10 to the 4/7 means that the statistical accuracy is already 1%, okay? Because statistical spread is a root. Okay, so in 2 minutes, I had 1% accuracy, which was wonderful, okay? So with this, what did we do? First, I repeated the experiment of the other people. So I don't describe in details, but the idea is the following. When you were discussing with theorists, there were theorists that would say, look, entanglement, we know it. For instance, in the helium atom, we know that the two electrons are entangled. If we would not write the fact that the two electrons are entangled, we would not have the right levels for the helium atom. But you know, my friend, my young friend, I was still young at that time, you know, my young friend, entanglement is a property of the microscopic world. When you go to macroscopic distances, it will disappear. I say, very interesting. What is a scale? What is a macroscopic distance? And then the guy would scratch his head and say, coherence length of the wave packet describing the photon. Perfect, because here the lifetime is 5 nanoseconds, which means a coherence length of 1.5 meters. So I pulled my polarizer at 6 meters from the source. Entanglement was still there, violation of Bell's inequality. So the violation of Bell's inequality that my colleagues have found at short distance, I found it at long distance. But it was still a scheme far from the ideal one. Now comes the gorgeous experiment. Well, the two gorgeous experiments. I could obtain, at that time, polarizer beam splitters. You are going to tell me, I can buy it on a catalog. Yes, at that time you could not buy it on a catalog. Between you and me, I had to bribe a friend with Philips labs in Eindhoven, and they produce it for me. And I say, how much do I owe? He said, you cannot pay. It's well beyond what you can pay with university. So I got it for free, or maybe a couple of bottles of wine and something like that. Okay, so I had real polarizers giving result +1 and -1. This was totally new. In previous schemes, they only had the +1 result. They did not have the -1 result. The big advantage is the following. In a single measurement with orientation A and B, you get the four numbers, plus, 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 minus, minus, plus, and minus, minus. So here, the measured coefficient of polarization is nothing else that this expression divided by the sum. It's a self-normalizing measurement. You don't need any accessory calibration. You know, the experiment is calibrating itself at each measurement. This is really a fantastic advantage, and with this, I'd like to, in the context of this metrology discussion, the curve which is here, the green curve, had been calculated before doing the measurement. It's a prediction of quantum mechanics taking into account the small defects of the experiment, that is to say, I had measured the small inefficiencies of the polarizer, and also when you have finite solid angles, there is a complicated calculation that shows that what you predict is a contrast slightly less than what is predicted in the ideal case. So the green curve is a prediction of quantum mechanics for the real experiment, and the boxes here are the result of the measurements with plus or minus 2 standard deviation. You see how beautiful it is. There is a perfect agreement with the result of quantum mechanics, between the result of the measurement and the prediction of quantum mechanics. Now, this curve also allows me to emphasize why it is rare that you can violate Bell's inequality. Let's suppose that you don't know about Bell's inequality, and somebody say, you should test correlation of polarization. What angle are you going to select? 0 degree, 45 degrees, 90 degrees. Okay, that's the first reaction. 0 degree, there is no conflict between quantum mechanics and Bell's inequality. 45 degrees, no conflict between, it's certainly not beyond 2. 90 degrees, no conflict. In fact, there had been an experiment of that kind with gamma photon emitted in the disintegration of positronium by people who did not know Bell's inequality. And because it was a very long experiment, they made a measurement at 0 degree, 45 degrees, and 90 degrees, nothing you could draw. If you don't know Bell's inequality, you don't know that you should insist on this point. But if you insist on this point, then you get a violation of Bell's inequality by more than 40 standard deviation. This is impressive. It's more than the Higgs boson, okay? Okay, last 50 minutes. I have 1 hour? Mr. Chairman, yeah. I have a chronometer here. It's an atomic clock, okay? And 15 minutes, I've thought. You remember, in order to have a real conflict with relativity, you want to rotate the polarizer while the photons are in flight. In my experiment, the distance between here and there was 6 meters, which represent 20 nanoseconds. So, can we rotate this, which is a big system with shield, lead, shielding, etc., 40 kilograms? You cannot rotate a polarizer of 40 kilograms in 10 nanoseconds or less, okay? So what we did is developing a switch here, an acousto-optic switch, that can either let light go straight or redirect light on the side. And so with this switch, which can switch every 10 nanoseconds, okay, then you send either the photon to a polarizer in orientation A or to a polarizer in orientation A prime. And this is equivalent to a single polarizer switch from A to A prime, back to A prime, etc. Same on the other side. The experiment is not perfect. The timing is okay. The timing is okay. We switch every 10 nanoseconds. It takes 40 nanoseconds to go from here to there. So the timing is okay. What is not okay is the fact that it is a regular switching. In an ideal experiment, you would dream of a random switching. We were not stupid. The generator here was different from this one. It was even a different frequency. This one was about 20 megahertz, this one about 25 megahertz. Moreover, there were not well-stabilized generators, so there was some kind of randomness between here and there, but it's not a real random number generator. We did the experiment. This is the acousto-optic switch that I had to build. No company could deliver, so I had to build it myself. And the signal was reduced, so rather than having a significant result in 2 minutes, it took half an hour. So we decided to stop to take the data when we had a violation of Bell's inequality by 6 standard deviation, which is significant. We could have continued to accumulate data, but you know, there were drifts and things like that. I think 6 standard deviation was really the meaning of our experiment. It was the first experiment where Einstein causality was enforced. So I told you there has been a third generation of experiment. To make a long story short, the big progress that was found in between 85 and 95, it took 10 years to develop the new source. The big progress is the following. In my experiment, the atoms are emitting photons in any direction of space. So you have to collect the beam in big lenses, and we have what we call in French a large étendue, okay, the product of the solid angle by the surface, okay? With a nonlinear process, parametric down conversion, you can enforce a phase matching condition in which you convince the photons to be emitted in a well-defined direction. So the photons are emitted in a small étendue, and then you can feed the photon into optical fibers. And once you have put the photon into an optical fiber, you can make experiments at a distance of tens of kilometers. Nicolas Gisin in Geneva is making experiments at tens of kilometers because he is allowed to use the commercial network of optical fibers at night. At night, Swiss people sleep, and Nicolas Gisin is doing measurements on the network. Zeilinger and Gregor Weiss in Innsbruck at that time made an experiment also with optical fiber, and they could implement for the first time a setup in which the direction of the polarizer was chosen by a real random number generator. They confirmed the result that I have obtained in 82. Okay. I don't want to detail the discussion about loopholes. What are loopholes? Loopholes are hypotheses necessary to be able to compare Bell's inequality test to the ideal Bell's inequality. There have been plenty of discussion. And people have shown that there were two possibilities that a hidden variable theory could give the result of quantum mechanics due to two problems. The first one was in the static experiments, the fact that there was a possibility of an exchange of information between the two ends of the experiment. This is named the locality loophole. The locality loophole has been closed by the experiment I did in 82, by the experiment that Zeilinger and Weiss did in 98. Okay. The other loophole is the fact that the detector of photons have poor efficiency, have quantum efficiency of 20%, 30%. So if somebody is a determined advocate of hidden variable theories, he can use the fact that many photons are lost to invent a theory in which the photons which are lost do not behave in the same way as the photons which are not lost, and so this is called the sensitivity loophole. The sensitivity loophole has been closed a few years ago by using this fantastic detector, like the one you are developing here with supraconductors detector. Now they have detector of photon with efficiency of how much? 98, 99%. Okay? So the sensitivity loophole has been closed. And then the advocates of hidden variable theory come and say, but the loopholes have not been closed simultaneously. So now there is an experiment which is being published, which has been performed in Delft, which is a complicated experiment with entanglement swapping, NV centers, and things like that. And I can tell you, I don't know if it has been published yet or not, but I know the preprint. They have the, between quote, ultimate experiment in which all the loopholes are closed simultaneously. They find agreement with quantum mechanics and a violation of Bell's inequality by only 2 standard deviations. So it's fine because it's a wonderful experiment. If we did not have all the previous results, nobody would believe 2 standard deviations. On the other hand, it's a beautiful scheme. They show that it is possible to make a test without closing all the loopholes, and I have no doubt that in the coming months and years, there will be more and more results on that. So we can conclude that Einstein's local realism is untenable, and to conclude, who is the chairman? It is you, the chairman? It is you, Massimo? Oh, well, that's okay, I can go on. No, this is very important. what should we conclude? We should conclude that local realism is untenable. And Einstein himself wrote what is a conclusion. So you should be surprised and say, oh, come on, Einstein did not believe in what he was expressing? Yes, he was believing. But he was making a reasoning ad absurdum. He would tell us, if I was not right, this is what would happen. But we know that in this case, he is not right. There is violation of Bell's inequality. And so this is what we have to conclude. Either drop the need of the independence of the physical reality present in different parts of space. When he says space, he means space-time, okay? Or accept that the measurement on a first system changes instantaneously, this is a word of Einstein himself, the real situation of the other object. This is called quantum non-locality. So Einstein tells us that we have to accept quantum non-locality. Some people call it quantum holism. It's very important for the following reason to understand these words. Quantum holism tells us that when I have a pair of entangled objects, I'm not allowed to consider that the property of the whole system is the reunion of the properties of the first one and of the second one. There is more in a pair of entangled objects than the sums of the properties of the first one and the second one. Why is it important to understand that? It's because it is at the root of quantum information. Quantum information is based in the fact that when you have entangled objects, there is much more in the entangled system than in the sum of the individual properties. So, in 1 minute, I show you what I had planned to say. Are we living a new quantum revolution? Quantum information is based on entanglement. So quantum cryptography with entangled pairs. So you know the idea of quantum cryptography, the two friends, Alice and Bob, and the awful eavesdropper who tries to intercept. And the basic idea is that the laws of quantum mechanics ensure the security. It's not a technical difficulty that you need to be computer to factorize number. It's basic laws of quantum mechanics which ensures the security. If you ask me a question, I can answer. Quantum computer, nobody knows if it will work, the quantum computer. Quantum simulation, it already works, in particular in the lab of Massimo. Quantum metrology, you all know the Virgo interferometer. If you use squeezed light, you increase the sensitivity of the Virgo interferometer. It costs less money to produce squeezed light and put it in the interferometer than building a 10-kilometer rather than a 2-kilometer interferometer. Atomic clock here. Gravimeter based on ultra-cold atoms. All this is quantum metrology. Here, NV centers to measure magnetic fields beyond the standard possibilities. So to make a long story short, I want to tell you that, in my opinion, the two ingredients which are at the root of this new quantum revolution is not only entanglement, I have emphasized entanglement, which is new and different from wave-particle duality, but it is also the fact that in the last decades, experimentalists have learned how to control individual quantum objects. This was beyond what people believed in the 50s. In the 50s, people thought you have zillions of quantum objects and you can make only measurement on big ensembles. But here, you know, AFM, atomic force microscope, producing single photon, trapping a single atom or a single electron, looking at quantum jumps, etc., etc. So the new quantum revolution, in my opinion, is based on entanglement and on the control of individual quantum objects, in contrast to the first quantum revolution, which was based on wave-particle duality and large ensembles. And if you remember what was the first quantum revolution, it was first conceptual, but it also gave us the laser, the transistor, the computer. It gave us the information and communication society. It was not only conceptual, but also technological. So you can ask the question, will quantum information and quantum technology lead to the quantum engineering society that we are going to discuss tomorrow in Brussels? The most likely roadmap is from proofs of principle with well-defined elementary microscopic objects, photon, atom, ions, to solid-state devices. It's fascinating. We live exciting times. I thank you very much for your attention.